Hello all, in today's video we are going to learn about a routing algorithm, distance vector routing. As we all are aware that the responsibilities of network layer include logical addressing and routing. What is routing? Routing is finding out the best path for delivering a packet from the source to the destination. So now let us know why is the algorithm named as distance vector routing. You know what is routing? Routing is finding out the best path from source to destination for delivering a packet. Here vector means we will maintain a table or a vector which maintains the least distance between the nodes. That is why it is named as distance vector routing. Here in distance vector routing algorithm, every node maintains a distance vector table. Distance vector table. That is why it is called as distance vector routing. This table maintains the minimum distances to every node. How these tables will help in routing packets? By looking into the table, we can find out that I can reach from one node to another in this particular cost using this particular route. This is the advantage of the routing table. Now let us take an example of a small network where this in the graph the nodes represent the vertices represents the nodes in the network and the edges represents the links in the network. The weight here is the metric or the cost for reaching from one node to another. You can see that if I construct a routing table for A, the cost from A to A is 0, the cost from A to B is 5, the cost from A to C is 2, the cost from A to D is 3, the cost from A to C, A to E is, I cannot reach it directly. So what is the next hop that I have to make? Hop is one jump from one node to another node. I will make a jump with a cost of 2 and then from C to E I will make a hop with a cost of 4. When I add these 2 plus 4, the cost is 6. That is A is reaching E with a cost of 6 via C. Let us now learn what are the basic steps in distance vector routing algorithm. The first step is initialization. In initialization, we will configure every node or the router in the network will configure its own routing table by maintaining the distances of itself to its neighbors. Then the second step is after you will initialize or configure your distance vectors, we will share these distance vectors to our immediate neighbors. Then next step is updating distance vectors. Upon receiving a distance vector from our neighbor, we will compare the distance to a particular node via my neighbor and I will update the shorter distance as a new distance. Then we will calculate the best path of reaching from source to the destination. Then we will have periodic updates. Periodic updates in the sense we will be sending and updating our distance vector tables every 30 seconds so that every node knows about what is happening in the network. Convergence. When we will stop doing these updations, when we are sure that whatever cost we have is the best cost or the best path for reaching from one node to another, then we converge or we come up to a final solution. Let us understand all this with an example. But before that, let us learn about the Bellman-Ford equation. As I told you that we are calculating the best path. When I told you this point, how are we calculating this best path or the least cost using the Bellman-Ford equation? I will tell you what is Bellman-Ford's equation. See, for example, I would like to calculate the best path or the distance from X to Y. I will take a minimum of over all the neighbors V of X as minimum of the cost of reaching from X to V plus the cost of reaching from V to Y. To better understand this, let us take up an example. I said I am taking a minimum over the path reaching from x to y directly, or using the neighbors distance from x to v, or added with the distance with v to y. If you have another neighbor, for example u, distance from x to u plus the distance from u to y. Whichever is the minimum distance, that path will be considered as the best path. See, with an example, I can reach from x to y directly with a cost of 6. So, I am taking a minimum of all the neighbors 6. Then, if I choose the neighbor v, the cost from dxv plus dvy, which is 3 plus 2. Or if I take the neighbor u, the cost is dxu plus duy, which is 4 plus 3. I will take a minimum of this, which is minimum of 6, 5, 7, which is 5. So I will select v as my neighbor for delivering the packets from x to y. This is about your Bellman-Ford's equation. Now let us take up an example. What is the first step? We will go according to the algorithm. The first step is initialization. We will initialize, every node will initialize its own distance vector table with the distances to its neighbors. Okay. A to A, the distance is 0. A to B is 12. A to C is 9. A to D is 4. Outgoing lines are A to A is A only, A to B is B, A to C is C, A to D is D. Okay. Let us have a look at the B's table. B to A, the distance is 12. B to B, it is 0. B to C is 1. But if you see, B cannot be directly reached. B cannot reach D directly. It has, so initially we will mark the distance as D, because we say that we cannot reach D through B. So we will mark it as infinity. Likewise, we will we will initialize the table for the node C and D. Now, so this is the initialized distance vector routing table. The next step is what? After initialization, we do sharing of distance vectors to the neighbors only. Who are the neighbors of A? Neighbors of A are B, C and D. So it will make use of the information of B, C and D, and it will update its routing table entries with the minimum distance. Now you see A to A is 0. Now if you can see that the distance from A to B is 12, it seems to be more. Let us make use of its neighbors. For example, C. C can reach B with a cost of 1 and A can reach C with a cost of 9. So if I add up this 9 plus 1, I can reach B with a cost of 10 via C instead of this cost 12. So how did it happen? Because I came to know that my neighbor C can reach B with a cost of 1. So what I am doing here, I am using the Bellman-Ford's algorithm here. You see here, I can reach from D, A to B either directly using A to B distance, or I will make use of the distance from A to C plus the distance from C to B. You see, either I will make use of the distance 12, or D from A to C is how much? 9. And how much is C to B? It is 1. So which is minimum? This is minimum. So what will I do? I will update A's table with the cost 10 via C. Okay. Then likewise you can see I can reach A to C with a cost of 9. If I take the help of my neighbor D's table, I can reach to D can reach to A with a cost of 4 and D can reach C with a cost of 2. So what I do here is, I want to reach from A to C. I will take a minimum of D directly from A to C or via D. Distance of A to D plus distance of D to C, which will come up to, either I take the distance of 9, or A to D is 4, A to D is 4 and D to C is 2. 4 plus 2, 6. So what I do, I will update my routing table with the new distance of A to C as 6 via D. Okay, so I will continue this for all the other tables also. B, if you can see, can't reach D directly. It will reach via, see here, B cannot reach D. So what we do is, we will see, it will take the help of the neighbor C. It knows that B can reach C in a distance of 1 and C can reach D with a distance of 2. So I will make use of 1 plus 2, which is equals to 3. So B is reaching D with a distance of 3 via C. Likewise, all the other tables using the information of their neighbors will update their routing tables. And this process continues. Now you can see further. A gets again next iteration. That was the first iteration. Now the second iteration. You can see A has again updated its cost from A to B as 10 to 7. How did it do so? It got the updated entry from the routing table D, which is one of its neighbor, which says that A can reach D with a cost of 4 and D says that it can reach C with a cost of 2. So 4 plus 2 is how much? 6. So A is reaching C via D with a cost of 6. So like this, all the routers will update its routing table entries, and then once, if I will do one more iteration, and in one more iteration what happens is, I come to know that I will converge. That means there are no more changes in the, this is the final solution and the final best path, so we will stop. So this is about your distance vector routing algorithm. This distance vector routing algorithm has a serious disadvantage called as the count to infinity problem. What is this count to infinity problem? The problem is due to instability in the network. See, as I told you, the routing tables only specify the information of the distance and the outgoing line. They don't tell you about the entire topology of the network, whether the node which I am connecting is alive or dead. All that information is not known to us. So let us understand this count to infinity problem, which is also known as two node instability problem. Let us take a scenario before failure. Before failure, if you see, X is connected to A is connected to B. A thinks that I am connecting to X with a cost of 2. B is assuming that it can reach X via A with a cost of 4 plus 2, 6. Okay. After failure, the problem here is bad news travels slowly, whereas good news travels faster. So here what happened, there was a bad news that the link has gone down between X to A and there is no other way of reaching X. So A will come to know that there is no, because it is its immediate neighbor, that A has X has gone down. So what it does, it updates its routing table with the value infinity, which signifies that it cannot reach X. But before A could pass this information to B, B passed its routing table to A, telling that it can reach X. It will not tell that I am reaching via A. It is not updating about that. It only tells that it can reach X with a cost of 6. So what A will think, okay, B can somehow reach X with a cost of 6 and I have a cost from A to B as 4. So it will add 4 plus 6, which is equals to 10. And then it will update its routing table. Again, this updation of A will periodic update. I told you it is periodic update. So this information will go to B, that A can reach X with a cost of 10. So what B will do, B will update its routing table telling that 10 plus 4, now my value is 14. Again, this information comes to A. So what A does, A thinks that I can reach X via B with a cost of 14. So it will again add 14 plus 4, 18, and then it will make it as 22, then it will make it as 26. Now this count goes down till infinity. That is why it is called as count to infinity problem. And this is happening because of the two nodes are unstable. They don't know that they can't connect to X until the value reaches infinity. This is due to the fact that the status of the link is not being shared periodically. This problem we overcome in link state routing, where we will, while we are routing, we will also share the link state information, whether the state of the link, whether it is on or off, whether it is up or down, it is being shared. So the problem of count to infinity problem will be avoided in link state routing, which we will learn in the next class. Thank you.